Welcome back. I first want to thank Nova Systems for sponsoring this session. This session is called Scalable Deep Learning for Large-Scale Scientific Machine Learning, Challenges and Opportunity. I'd like to introduce our speaker, Brian. Brian Van Hessen is the Informatics Group Leader and Computer Scientist for the Center for Applied Scientific Computing at Lawrence Livermore National Laboratory. Thank you, Brian, for being here.
Thank you very much, Angela, and thank you for the opportunity to speak to the conference here. I really appreciate the invitation, and I do wish we could be here in person and actually mingle and rub elbows, as it were, but I hope to have a dynamic talk today and a chance to interact with you through the question and answers. As mentioned, I want to talk to you about some of the challenges we see when we really think about large-scale scientific machine learning. What are the issues we face at Lawrence Livermore National Lab, as well as other across the Department of Energy complex through many of our partnerships. And so I've broken my talk down into sort of 3 vignettes where I'm going to identify several challenges that we have faced, and these are not unique to us alone, but we see these in the academic and research community, but also just methods that we're using to actually tackle these. And so I'll give you example problems as well as some solutions, and these aren't the only solutions, but these are the ones that we've been pushing forward in our research. So the challenges that we really see are, we have these massive data sets where you might have billions of compounds, billions of samples that you need to process to train your deep neural network and your models. And the problem is that traditional data parallelism really is limited when you go to large mini-batch sizes. So we need to think about novel ways to compose parallelism, not just data parallelism, to be able to actually train models on these very large data sets. And we'll give you an example of that in a few slides. Another challenge is very large sample sizes. What happens when you look at large 3D volumes where the activations of a single sample don't even fit on a single GPU or compute node? And there's techniques we've developed with distributed convolutions and for halo exchanges where we exploit model parallelism to be able to parallelize the training of these neural networks across multiple GPUs. And finally, large models. What happens when the models don't even fit on a modest number of GPUs or compute nodes? We see this with transformer family. And so we have developed methods for subgraph parallelism where we can split the model compute graph over multiple resources. Now, these problems are not unique to the examples that we're giving, but they are actually generally applicable to the wide class of scale of scientific machine learning. I'm going to start by talking about some work that we did that was part of a Gordon Bell submission. We were a finalist at SC 2020, where we looked at pushing how we can work with billions of chemical compounds. And this was work that was in collaboration with the XLearn and ATOM projects at Lawrence Livermore National Lab, as well as the ASC program, where we were looking at how can we develop generative models for small molecular drug design for COVID-19 research. This was the primary research team that conducted this work, and I want to give thanks to them for all of their effort. And we were able to achieve a Gordon Bell finalist with this work at SC 2020, as I said. Throughout the rest of the talk, you're going to hear about a lot of research from a large number of people. I happen to have the opportunity to present on all of their behalf, and I did want to just call out. We have a number of researchers at Lawrence Livermore National Lab, as well as collaborators both at other DOE national labs, other departments of Lawrence Livermore, but also a healthy student pipeline that we work with. So thank you very much to all of their efforts on this research. So I'm going to talk to you in our first vignette about training at scale, where we wanted to train on a data set that had 1.613 billion chemical compounds, and we wanted to use all of the Sierra supercomputer at Lawrence Livermore National Lab for that, and that's 16,640 GPUs. And so how did we do this? Well, it turns out that we can't just scale up PyTorch or TensorFlow to do this, because we need something that's fundamentally distributed from the ground up. And so for a number of years now, we've been developing a deep learning toolkit called LBANN, the Livermore Big Artificial Neural Network Toolkit, that is designed as a distributed memory algorithm for these training and inference tasks. It is built on two distributed tensor and linear algebra libraries, dihydrogen and hydrogen, that are both GPU accelerated, as well as a high performance GPU aware communication library, Aluminum, that we've published about all of these in previous years, talking about how can we really exploit the leadership class supercomputing that is available to us. These toolkits are based on a C++ with MPI and OpenMP foundation, and they take advantage of CUDA, cuDNN, Nickel, and now we've pulled in ROCm, RICL, and 1DNN. So we can run on everything from a standard NVIDIA-based platform like Sierra to emerging systems like El Capitan and even Fugaku. All of the code is open sourced. It's on GitHub. The links are posted on there, the right, because we want to make this this toolkit available to the research community. It has a PyTorch-ish front end where you can describe your model in Python, but fundamentally it is a batched execution algorithm designed for traditional HPC resources. And we're developing, always developing better ways to exchange models with tools like PyTorch. So the idea is that you prototype neural networks that you're interested in PyTorch or TensorFlow, and then you can scale them in a tool like LBANN. Okay, so for this first vignette, what the task we wanted to do was be able to identify or create a generative model that would be able to generate small molecule chemical compounds that would be used to target both viral entry and viral replication of the SARS-CoV-2 protein. And so the idea is that there's this massive drug design pipeline called the GMD that was larger than the effort that I'll talk about. But what we're focusing on is being able to create new chemical compounds, because a brute force search of chemical compound space is just intractable. There's on the order of 10 to the 60th chemical compounds. So we want to be able to enable lead compound design. So how does that work? So as I said, we want to be able to train a molecular generator with more chemical compounds that are all synthesizable so that we can have a larger chemical diversity of the proposed solutions. And the idea is shown down here in this block diagram, where in the middle is a molecular generator. This is actually the work that we trained for our Gordon Bell finalist paper. And it is a pair of an encoder and decoder, but it's actually pulled into a larger molecular design loop where you have a molecular optimizer and you actually have other components around that I'll show in the next slide. But the goal is, if we have a chemical compound that we like, a lead compound, and that starts in our chemical space, if we push that into our molecular generator, we get some latent representation. We then use another model to perturb that to be able to optimize it for different chemical characteristics. These could be different pharmacokinetics, maybe increased synthesizability, better efficacy, better safety, different opportunities. But then we perturb that in latent space, and we are going to project that chemical compound back through the decoder and create a new proposed chemical. Now, this is all great, but the hypothesis of this work that is, if you use a larger chemical space, if you train the molecular generator on more information, you'll get a more diverse set of proposed solutions. So to do, and the idea here is, of course, is that if you start with a chemical you know about, but you train on this expanded chemical space, the generator can be more creative, as it were, and hopefully lead to novel compound discovery. So how does this work, and what was the challenge? So the challenge, so up here in the block diagram is the block diagram of the generative molecular design loop, the GMD loop from the ATOM project, where you have a working compound library. You do some compound evaluation to figure out what your lead compounds are. You're going to do some design criteria to help to figure out how you want to optimize it, and then you're going to go through this generative model that's in the bottom block here, shown in green, where you're going to want to propose new molecules. And again, our work focused on how can we train a more effective generative model. Well, the state of the art prior to what we did was to use a junction tree variational autoencoder, but this is really slow to train. Using a data set with only a million chemical compounds and implemented in PyTorch, it took about 24 hours to do a single pass of the data, a single epoch. And so that's not terribly efficient. So what we wanted to do was identify a new way to do a more scalable neural network architecture, and we actually went back to a set of character-based sequence models that the community had looked at before, and we actually innovated on that. And so the idea is you want to be able to take your chemical compound, and we need to turn into a character sequence now. So we're going to look at the SMILES encoding, which is shown here, where you can take sort of this standard chemical representation, a 2D graph, and turn it into a sequence of a character string. You're going to train the neural network on that character string. You're then going to be able to, as I said, push a lead compound into that latent representation, perturb it, and then decode it into a new chemical compound. And if you do this effectively, you'll be able to get molecules that are close but not identical to the original lead compound, which is the exploratory part of the research. And to measure that, we're going to use something called the tandem similarity. It's also referred to as the tandem distance, where you can score how close they are in chemical space. Okay, so to do this, we developed a new character-based Wasserstein autoencoder that is a class of autoencoders that addresses many of the challenges previously seen with both character-based autoencoders and variational autoencoders. The idea my research colleague Sam had was take what you see within Wasserstein autoencoders and apply it to this type of model. The model here is shown on the right, where again, we have this input sequence on the bottom. We go through a gated recurrent unit. We then go through a full, that generates the encoder. We go to a fully connected layer. That then produces the latent representation and goes back out through the decoder and gives us an output chemical compound. And we add this discriminator here because that allows us to actually ensure both better reconstruction, but also variational sampling from that latent representation. The challenge with a standard variational encoder is it didn't allow the lead character optimization, and that was the insight for the model that we developed. So this model allowed us to actually do the lead optimization design, and it was actually very successful. But the challenge to train this on 1 billion chemical compounds is that the model itself is not very large. You can't get very far with just data or model parallelism. You actually need a whole nother type of parallelism. And we leveraged some research we had done on a tournament algorithm that allows you to train a single instance of a model on a massive data set. We published this previously in 2017, 2019, but this really allows you to use an entire supercomputer to accelerate the training. The idea is that you have multiple trainers shown down here. I have 4 of them, each with their own data partition. So an independent silo of the entire 1.6 billion chemical compounds. And you're going to take instances of the model and you're going to train them. And then periodically, you're going to exchange your model with a random peer. So after some amount of training, an epoch or 2, you have a set of partially trained weights. You're then going to exchange that with a different partition or different trainer every single time you do that, you pick a different random peer. You do a tournament with a held out set of data, and then the most successful models are propagated, and those trainers adopt those models and continue evolving them over the training sequence. What happens then is you essentially get the best model does a tour of the different silos of data. And what we've shown previously, and in this work as well, is that the winning model at the very end is actually able to generalize across the entire data set and the entire held out test set. But the key thing is that we're able to maintain scalability through multiple levels of parallelism that are composed. Within the trainers, we use both model and data parallelism, so we have collective communications, and these scale, in this case, up to about 16 GPUs, 4 compute nodes. But between trainers, we're able to use point-to-point communication, which really allows us to scale to all 16,000 GPUs, 4,160 nodes of Sierra. And so you're really leveraging the advantage of scalable peer-to-peer communication. So what did this allow us to do? Well, we were able to use LBANN to train this character-based Wasserstein autoencoder on a data set that was just previously unattainable, and do it with a quality of model that was well within the range of what the domain scientists expected. So on the top right here, I show in this table how as we improve the test error of the trained model, we not only increase the % of valid chemical compounds that are proposed, but also we're able to reduce the average tandem modal distance of the proposed chemical compounds. And we're looking for a sweet spot. So working with our domain scientists, we found that achieving a test error of about 0.024 gave us a model that was substantially better than what we had previously done with the junction tree variation autoencoder, and actually was trained on this data set that's 1,000 times larger. On the right-hand side, on the bottom right-hand side, we're showing a plot where we show the scalability as we go from 64 compute nodes to 4,160. We see that the time per epoch drops linearly with the amount of compute resources brought to bear, and this is to be expected because of the way the asynchronous LTFB algorithm works. But we can actually see that as we train with more compute resources, we do take more epochs because you see less and less data per epoch per silo, but we're able to achieve that 0.025 reconstruction error with at all scales, so we don't fall off as we get to larger scale. And we actually are showing the results both in blue with 8 GPUs per model and with 16 GPUs per model as well. It turns out that, again, as you change the number of models, you have less data per trainer, and so sometimes you need more training epochs. But as you see here, the number of epochs is highlighted. We say 0.025 at 48 epochs. We're able to get all of the models to converge. So now, what does this mean about time to solution? Well, so on the right-hand side here, we show the total wall clock runtime of training this model from scratch with 1 billion chemical compounds, and versus the test error on the y-axis. And we show results going from 64 compute nodes on the gray bar all the way at the right-hand side of the plot, all the way to 4,160 at the left-hand side of the plot, shown in red. And what we see is that going from 64 compute nodes, 256 GPUs, to 256 compute nodes, 1,000 GPUs, we're able to achieve a 1.8x speed up to get to that required test convergence value of 0.025, which is a parallel efficiency of 44%. So that's pretty good given the size of the model. And really what's important is where before we were training using a junction tree variational encoder, 1 million chemical compounds in 24 hours, we're now able to train with 256 compute nodes in 32 minutes on 1.613 billion chemical compounds. So 3 orders of magnitude more data, and we're now doing this in minutes. So the time to insight about whether or not the model is working, whether or not we get good reconstruction, is now human limited, not compute limited. We did drive this all the way to the full system scale where we went to 4,160 compute nodes, and we were able to achieve 17.1% peak efficiency of the Sierra supercomputer. So that's roughly 318 petaflops in mixed precision. We did only achieve an 18% speed up over 2,000 compute nodes at 4,000. So our parallel efficiency was substantially lower, but we are able to actually demonstrate that you can train this in 23 minutes. And this really unlocks new opportunities for how do we train at scale, which is some of our future work I'll touch base on at the end. But I just want to highlight that the ability to operate with leadership class computing at this scale really unlocks a new frontier for neural network architecture design, whereas my colleague Barry Chin always like to say, we want to fail fast. We want to be able to take new models, train them quickly, not wait for weeks or months to figure out whether or not the model converge, but do so in real time to accelerate our researchers' productivity. So that was really focusing on one of the big challenges we see, which is massive numbers of samples in our scientific data set. But now I'm going to switch gears and talk about what happens when we have very large sample sizes. So as I said, the challenge is what happens if the neural network activations or information for a single sample don't even fit on a single GPU. So here's an example: is we have a large scale we have these large scale supercomputers. We have Sierra shown here on the bottom right. We have this data volume, which is a cosmological data set. It's 512 cubed with 4 channels and 2 bytes per element. So each sample is a gigabyte in size. You might say, hey, we ought to be able to train that. And with standard approaches, you actually cannot. The regression model that came out of our colleagues at Lawrence Berkeley National Lab, the CosmoFlow, let alone the CosmoGAN model, simply don't fit on these leadership class GPUs. And so you could subsample it and look at smaller volumes of it, but it turns out that loses information. The model is unable to learn long-range characteristics of the data set that are actually really critical to understanding some of these cosmological parameters from the CosmoFlow model. So what do? Well, we take a playbook from our HPC background and we look at how can we parallelize with different techniques. So we have sample data parallelism that's very common in the community. That's very effective. We use some of that. But now we're going to mix in spatial parallelism where you actually partition this data, in this case, this poor penguin, we partition it up over multiple GPUs and we use a halo exchange to be able to ensure that mathematically we're computing the same result. This is well known within the field of HPC computing, but was novel to scalable machine learning when we published it in 2019. We've then extended that as well to both channel and filter parallelism. So you can now parallelize again along all dimensions of these kinds of large models. So what does this mean? So when we talk about spatial parallelism, we have a compute node from Sierra shown here with 16 gigabyte Volta V100s, and we have 4 of them per compute node that are highly interconnected with NVLink. And so the idea is that we have this volume, and we now want to put slabs of it onto each GPU, and then again do the halo exchange so that the result that you compute is the same as if you had done it on a single larger GPU. And this, we may say, well, hey, we have 32 gigabyte, 64, or even 80 gigabyte Ampere models. Well, that's fantastic, and that may hold this instance of the model. But these domain scientists, they're power mad. They really want to get as large as they can. So because they're simulating the universe. So it turns out that if you say, well, we can simulate a 512 cube universe, they say that's great. We want to go to 2048. We want to go larger and larger. And so the appetite for this kind of parallelism is really limited by what the tools and technology can give us. But the need for these larger volumes, not just within cosmology, but within other hydrodynamic codes, combustion models, all sorts of models, climate models across the community really have an appetite for these much larger data samples. But what were we able to do? So here is an example of our scaling where we were able to show on the left-hand side the throughput on the y-axis for both plots and the number of GPUs on the x-axis. The first on the left-hand side was using a smaller 128 cube data cube. This is actually something that we could do with mesh TensorFlow on a single node, but we were not able to scale to the 512 with mesh TensorFlow. But what we see is that we're able to get a 65x speed up using 512 GPUs versus 4. So a substantial improvement without loss of generality. In fact, in a different talk, we've shown that the quality of this model is an order of magnitude better than the standard CosmoFlow model when we go to the 512 cube data volume for 2 of the cosmological parameters. And that the performance of that is shown on the right-hand side, where again, the activations required are 53 gigabytes per sample, so way too large. But so you actually have to partition this, and this is a hybrid data spatial parallelism, 8-way, so 8 GPUs per sample. And that's per sample, and we have some data parallelism mixed in there as well, and scaling up to 248 GPUs, we see extremely good strong scaling of the problem, or scalability of the problem. Sorry, not strong scaling, because we're adding more work. Sorry, for the last part of the talk here, I want to look at what happens when we look at large models. So what are the challenges when the model weights don't even fit on a modest number of GPUs or compute nodes? Now, this has happened with other models before, but there's a whole family of models that I'm sure everybody in the audience is very familiar with that exacerbates this and really is driving a large area of the research in the community right now. And these are the transformer models. The fantastic thing is that these are really tackling spaces where other sequential models like the gated recurrent unit or the LSTM were able to train on large sequences, but were not as scalable and actually had challenges with parallelization. So it turns out that the transformer is analogous to a convolutional model being spread spatially across an input sequence, and it actually affords a much more parallelizable implementation because of one of the key techniques, which is multi-headed attention. So in the block diagram here, we have an input sequence on the bottle. You bring that data in, you slice it up, and you put it into the independent attention heads that are replicating the same computation, and then are all brought together at the very top of the compute graph. It turns out that each of these attention heads is an independent parallel subgraph that can be partitioned across multiple compute resources. And by doing this, we're actually able to strong scale the time to training. And these models can also get into the billions of parameters when we look at models like GPT-3 and other in the family of transformers. And this is work that was published by our team at IPDPS in 2021. So the idea here is that you can, as I said, you're going to want to partition it so that different GPUs, different MPI ranks are managing different parts of the transformer model. And this then partitions the work into both intra and inter GPU communication, which of course really leverages the architectural characteristics of these leadership class HPC resources. Okay, so if you do this in a vanilla way, you just say, we have this data flow graph here shown on the top right with 10 compute layers, 2 common layers that are the fan in, fan out, and 8 layers in between. And we want to partition those across multiple GPUs. The problem is you get a huge amount of imbalance. So the vanilla subgraph parallelism does not work well, primarily because in this example, if you have 32 samples going for your mini batch size, you need to have 32 samples on all of these, and that makes GPU1 a bottleneck. So what can we do? Well, we can use data and subgraph parallelism, where for the common layers, layers 1 and 10, we exploit data parallelism, where every instance of layer 1 and 10 only works on 8 samples out of this 32 sample mini batch. But because of how we want to parallelize layers 2 through 9, we actually have 32 samples per layer on each GPU. And this allows you to actually get much, much better load balancing. But you still, and actually really helps you avoid over decomposition of any one of the single layers. And so this is a substantial improvement, but there is actually an opportunity for even more improvement if we look at the proximity and we do a topological aware design. So it turns out that if you do this in a naive way, where you have the subgraphs and the subgraph mapped evenly across the compute nodes, you'll get this top left communication pattern, which maximizes sort of the number of inter-GPU communication resources, which is always slower than intra-GPU communication resources. If you do a topology aware data and subgraph parallelism shown on the top right, you can reorder how the jobs are assigned to GPUs, and you get much better communication patterns. But when you go down to the bottom left with the subgrid and the common layer subgrid partitioning, you need to actually address it slightly differently. So to avoid the bottleneck that we see in the bottom left, we want to go to a topology aware data and subgrid parallelism with common sub layers, and that gives us our optimal design point here. Using this, we evaluated the performance for a GPT-2 neural network up to 512 GPUs, and what we are able to see is that we can get a 1.4x speedup relative to just pure data parallelism, and this is represented on the graph here as we go to more GPUs with a improved time per mini batch shown on the y-axis. And this actually is showing the trade-off between data and subgraph parallelism with common sub-expressions, as well as, but actually this is not showing the topology awareness. That's in the next slide. So actually it is, sorry, I apologize. But the other thing it allows us to do is really focus on subgraph parallelism where you do strong scaling. So this is showing the classic attention is all you need transformer. And what we wanted to do was actually partition the work over more GPUs to be able to train the same size model faster. And this is really important because, as we all know, if we increase the amount of data parallelism, sometimes we get a degradation in learning. So exploiting as much strong scaling is really critical. We see on the the left-hand plot here, as we go from 4 to 16 GPUs, our time to mini batch is time per mini batch is cut in half when we use the data in subgraph parallelism. And on the right-hand side, this is shown on the LBANN system, which is an unclassified version of Sierra, we're able to see that we can accelerate the time to convergence pretty substantially, shown as the blue triangles versus the red blocks. So that allows us to, again, to just bring more resources to bear without actually impacting or degrading the quality of learning. Okay, so I mentioned there's a couple of future next steps and future challenges. One of the things that was really highlighted in our work with the ADAM model, the character-based Wasserstein on all of Sierra, is that as we scale to the entire system, we're able to accelerate convergence, but not in a manner that's commensurate with the number of compute resources brought to bear. Part of this was that the model just didn't learn faster. So there's a lot of techniques about parallelization, but one of the key things we wanted to look at was what if we brought scalable second order methods to bear? So we're working with some colleagues who developed some scalable K-fact methods, and we're implementing them with a new type of parallelism, an extension of our subgraph parallelism, so that we can actually essentially add second order K-fact calculations and gradient updates with minimal impact on the time to train over a first order method like basic SGD with momentum. So that's work in progress. The next, another big challenge is there are complex models based on graph neural networks that don't scale terribly well because of the high interconnectivity, yet the fair degree of sparsity in these graph models. And so we're looking at both ways to repose the algorithm as a more dense variant that allows us to better exploit the core characteristics of GPU accelerators, but also apply other methods of model parallel training for graph neural networks, graph convolutional networks, edge conditioned graph neural networks, that whole family, and that will really unlock whole new scientific models. Okay, so to conclude, scientific machine learning has a number of challenges related to the number of samples, size of models that make it a really exciting field to play in and really focus our energies at. We've made a lot of headway by being able to compose multiple levels of parallelism in a distributed training algorithm that really enables leadership class HPC systems to train these neural networks more rapidly. As a showcase piece, we were able to achieve 318 petaflops of mixed precision, which was 17% peak performance of the Sierra supercomputing. And that was really an exercise in balancing the tournament and data parallelism to fine-tune both the best performance, but also the rate of learning. A lot of this really requires scalable data ingestion and distributed in-memory data store to be able to ensure that you're not killing your parallel file system or I/O bound, and that's a critical aspect that often doesn't get in as much showtime as it should, but it's incredibly important. And finally, actually, as a funny story, you have to explore asynchrony at these large scale to avoid significant impacts at power on these leadership class systems, where you can actually get the local regional power operator calling up your supercomputing center going, what the heck is going on, when you have a 4 megawatt power swing. But finally, the critical aspect is that the ability to operate at this scale really unlocks a new frontier for neural architecture design and the application of scientific machine learning, where the ability to rapidly train and retrain on both new data sets, but new architectures and new hyperparameter exploration really allows you to debug neural network design and the scientific application of them into tens of minutes, not weeks, for time to insight. And so our work is in the open source. We love working with academic and industrial collaborators. We've published all of this at various venues, mainly in the supercomputing IPDPS venues, as well as the International Journal on High Performance Computing. And with that, I would like to say thank you very much for the invitation, and I will take any questions.
Hi, Ryan. Thank you so much. I think one thing it stood out to me is like how many different applications that you pursued: drug discovery, cosmology, language models. Are you seeing ways to repurpose what you've learned in completely different areas?
Yeah, absolutely. I mean, and so fundamentally, the techniques we've developed across the years generally find a home where they start with a single exemplar application and they migrate across a variety of these. So, for example, one of our most recent work with subgraph parallelism for the transformer models, that really is looking at how you can take the compute and data flow graph, isolate regions, and parallelize it very effectively. That also has implications across the scalable second order methods, where if you think about computing the inverse matrices which is the expensive part of that, that can be done on a completely subgrid of resources. And I switch between subgraph and subgrid because subgrid refers to the independent compute resources. And you can marry those two grids together to basically be able to train your model with minimal impact, as long as you can bring more compute resources to bear. Similarly, we are able to look at new methods with GAN training, where we look at multi-GAN with multiple discriminators and that help avoid mode collapse. And each of those can be put on a separate compute grid. So that's just an example where the computer science that meets the machine learning and can be generalized very effectively across different applications.
Question from the audience: can you elaborate on the metrics you use to evaluate the end result with parallel training versus not?
Yeah, absolutely. So really that does come down to the metrics that the domain scientist has outlined. So that for visual models, that's typically top one accuracy on a classification problem like ImageNet. For the SMILES, for the character-based Wasserstein autoencoder, is really achieving a certain tandem-modal similarity. For the transformer models, there's the blue score and other things. So our effort is that when we train these models with these scalable methods, is that we don't degrade those primary metrics. And then we're able to look at the time to solution to achieve that level of quality. And so, obviously when we strong scale, you add no more work, you just add more compute resources, so you parallelize it more, and you really are fighting against communication latencies and bandwidth. If you add data parallelism, that's a really tricky one, because as you add a larger mini batch to process your data set faster, typically you have to tweak your learning parameters. And so that's not as easy to do. But when we look at the tournament model, we actually don't change the learning metrics. We actually require you to meet the same quality to say that we've converged the model.
Well, Brian, another question from Mauricio. High order optimization is not only about KFAC. Thinking on other approaches?
Yeah, absolutely. You're right, Mauricio. KFAC happens to be the vein that our collaborator, Ryo Yokata from Tokyo Tech, has been focusing on. And so in collaboration with him, because we're not experts in second order methods, we've been focusing on taking his research algorithm and being able to parallelize it. But the framework should be able to work with other second order optimization techniques. You're absolutely right. That just happens to be the stallion that's in our stable.
Well, thank you so much, Brian, for speaking today. Hopefully we'll get to have you in Houston sometime soon.
I appreciate the invitation, and I do miss not being able to come out and travel, but thank you for the opportunity.
Yeah.